I like example 1. I like example 1. Example 1 is a nice question. Suppose an asteroid is traveling at 5.67 times 10 to the 4th meters per second at a distance of 1.2 times 10 to the 7th meters from the center of the Earth. Is that an altitude or is that a radius? Psst, okay, put it away, thank you. It's a radius, so I don't need to add the altitude, the radius of the Earth to this. How much kinetic energy would it have if it impacted the Earth? How will I solve this? Caleb, is this question asking how much work?
No.
So I don't need to, I'm not going to start out by going work equals change in potential plus change in kinetic. Although it is mentioning energy.
Yeah.
Is there a change in height in this question? Is there going to be a change in speed?
Yeah.
Is there a yucky curvy force?
Yes.
So this is going to be conservation of energy. G. I'm going to start out by going an asteroid impact question is going to be on, or some type of impact question is going to be on your test. And I'll tell you what parts I could ask you to find. Here I was mean, because are we starting out at rest? No, if I was nice, I might have said that just to give you one term to cancel out. Is potential energy ever going to be 0? Isn't it 0 on the Earth's surface?
Yeah. No.
So are we in outer space? Is this question here, are we in outer space?
No. Yes.
So where is 0 potential energy if we're in outer space? Out at?
Infinity.
So are any of these 0? Now, if I was nice, I could have said, instead of saying a distance of 1.27 meters from the center of the Earth, I could have said starts a very, very, very long distance away. Then you could have said, oh, I'm far enough away that my initial potential is 0. And I might do that on one version of the test. I don't know. But right now, I don't think any of these are 0. Now, it wants me to get the final kinetic energy by itself. I think I'm just going to minus that to there. But you know what? Before I do that, let's plug in our equations. So initial is going to be a half mv initial squared plus negative big G, big M, little m over r initial equals, I'm not going to write a half mv squared because A actually doesn't want me to find V, it wants me to find the kinetic energy. So I'll just leave it as the kinetic energy. Plus negative big G, big M, little m over our final. Now I think I'm going to choose to plus that to that side. I'm going to get a half m v initial squared minus big G, big M, little m over r initial, but plus big G, big M, little m over r final. That's going to tell me how much kinetic energy we have when we hit the ground. Should I be expecting a positive answer or a negative answer here? In fact, I think a fairly big positive if I understand asteroid impacts at all. So if I get a negative, I've messed up somewhere. I'm going to be really, really careful. A half m. Now, you might be saying, Nate, look, isn't there an m in kinetic energy? Isn't there an m in everything? It won't cancel. And if they had said find V final, sure, I would have canceled out the m's, but since they want me to get this by itself, that still contains the mass because kinetic energy depends on your velocity squared, but also on your mass. So unfortunately, the m's aren't going to cancel. So it's going to be 45,000. What was my initial velocity? 5.67 times 10 to the 4th. Squared. That's pretty fast. That's 56,700 meters per second. I might have overdone it, but I wanted to have a spectacular impact. Minus 6.67 times 10 to the negative 11. Are we around the Earth, or does the question say a different planet? 5.98 times 10 to the 24th. 45,000 our initial, and it was a radius they gave us because they did give it from the center of the Earth. So 1.2 times 10 to the 7th. I need a little bit more room, Mr. Duke. This is why I love this tablet. There we go. And then there's going to be a plus sign, ditto mark times ditto mark times ditto mark divided by 6.38 times 10 to the 6th radius of the Earth. That equals kinetic energy final. I can't even fit it on one line. Holy smokes. Let's crunch the first term to like 5 sig figs. So I get 7.2335 times 10 to the 13th. Holy smokes. Is that right for the first term? Yeah, 7.2335 times 10 to the 13th. 7.2335 times 10 to the 13th. And there's going to be a minus. Well, that's good. We'll take that. 6.6. Oh, negative, Mr. Dewick. 6.67 times 10 to the negative 11. 5.98. 5.98 times 10 to the 24th times 45,000 divided by, what was it? 1.2 times 10 to the 7th. I'm missing a 1. There, I think I got it. 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 45,000. Do you get negative 1.4957 times 10 to the 12th? That's at least losing energy. 1.4957 times 10 to the 12th. Plus, now we're going to cleverly backspace and edit. I delete the negative sign, and instead of 1.2 times 10 to the 7th, 6.38 times 10 to the 6th, 2.8133 times 10 to the 12th. That equals my kinetic energy final. Add them up. You know what? This is big enough that it should be in red. All right, I got that number. Plus negative 1.4957 times 10 to the 12th. Plus positive 7.2335 times 10 to the 13th. No typos. I don't want to make a typo here. Do you get 7.365? 7.37 times 10 to the 13th joules? Sorry, I wrote that down wrong. Yeah, 37 times 10 to the 13th. Now that you know that, could you find V? Sure, times by 2, divide by m square root. And that's probably what I'd ask on the test. Just to put it in perspective, turn the page. What was the atom bomb over Hiroshima? How many joules? So, it's a little more than an atom bomb. You got 10 to the matches. So this would be like basically having an atom bomb hit somewhere. Preview of coming attractions. Now, what advantages, what protects us? Well, first of all, Jupiter acts like a giant solar system vacuum cleaner. Jupiter gets lots of asteroid and other debris impacts all the time. And the sun is a pretty good vacuum cleaner. The Earth's gravitational field, thankfully, just isn't that big. And those smaller objects that tend to make it through tend to burn up in our atmosphere, but you're all young enough to remember the Russian meteorite about 5 years ago that exploded and people got injured because the sonic boom blew out windows and things like that. So it happens. I'm going to say around 1910, there's an area of Siberia where there must have been a massive meteor explosion in the air because for miles around in all directions, all the trees have been blown down. Conspiracy theorists will say it was aliens and some kind of a UFO testing an atomic bomb. No, it's garbage. There was an asteroid impact that exploded in the air, and with a lot of energy. Oh, how fast would it be traveling at impact? So, KE equals a half mv squared. So V is going to be 2 times the kinetic energy divided by m. It's going to be 2 times 7.365 times 10 to the 13th divided by, was the mass 45,000? No one's looking. I'll check. Yep. I'm going to use my answer button, of course. So 2 square rooted. Sorry?
No, I'm just wondering because the KE, isn't it 6.3?
No, that's Hiroshima.
Oh,
That's an atom bomb. I want the one from the previous page.
Okay.
So it's going to be 2 times, but I almost forgot the square root. That would have been a little awkward. Divided by that square root. Probably, in fact, definitely, at this speed it wouldn't make it through the atmosphere, but there would be some pretty solid sonic booms and atmospheric things going on here. 57,000, so 5.7 times 10 to the 5.72 times 10 to the 4th. What was it going initially? 5.67 times 10 to the 4th. Actually didn't gain that much speed because I had it going so fast to begin with. I need to tweak these numbers a little bit. But I wanted to give you an idea of roughly what an atom bomb's worth of impact would be. Geosynchronous satellites maintain their... We already watched the Neil deGrasse Tyson video. Geosynchronous satellites maintain their orbit over the same place on Earth at all times. What's the period of such a satellite? Well, if you're the Earth, how long does it take the Earth to spin around?
365.
No, that's go around the sun.
4 hours.
24 hours? And so if I want a satellite to appear as though it's staying above the same place at all times, what would I need to make the period of the satellite? So it's going to be 24 hours, which is 24 times 60 times 60, which is what? I think 86,400, but don't quote me. Same as Earth on your formula sheet, right? It says the period of the Earth is 86,400. It says the period of the Earth is 86,400.
8.61 times 10 to the 4.
6.1. It says 86,100.
It says 8.61 times 10 to the
But we just crunched the numbers. We got 86,400. Have you been lied to all your life? Is the Earth's period actually not 24 hours? We lied to you?
Is it the time zones?
Pause for a second. What's the radius of such a satellite?
I think I'm gonna find out.
Are we in orbit?
Correct.
How do you know?
Because it says orbit.
Gravity big G, big M, little m over r squared is what's pulling me in a circle m. Which version of A am I going to use here? They don't need to tell me the mass of the satellite, although they could. Sometimes I will in the questions, sometimes I won't. What are we trying to find? Does an R cancel this time?
No.
Ooh, someone said yes, someone said no. This is the most common mistake. Kieran, you're not on your phone behind that binder right now or anything, are you? It'd be foolish if you're typing away like that and I could see your hand moving on some kind of electric device. That would be foolish. Put the phone completely away if there's a phone hidden back there. If it was your calculator, I apologize for falsely accusing you. Does the R cancel? It does not. The R is going to move up to there, and we're going to get an R cubed. And there's going to be a big G, big M. The T squared moves over there. And the 4 pi squared, I think, moves to the bottom. And then, oh, we've seen this before, but not for a while. How do we get rid of a cubed? Alrighty. Let's crunch this. It's going to be the cube root of... Mr. Dweck, what? Instead of writing 6.67 times 10 to the negative 11, because it's a constant, can I just write a big G? You can, I guess. I usually write it out just to be paranoid. Just don't mix up big G and little g. Little g is the gravitational field strength, which on the Earth is 9.8, but you now have a universal way to calculate that, too. So I'm going to write the 6.67 times 10 to the negative 11. You going to make it, Lena? Because you were laying down there for a bit, my angel. I'm going to use 86,400 squared all over 4 pi squared. And I get to use my cube root button. 6.67 scientific notation times 5.98 times 10 to the 24th times 86,400 squared divided by bracket 4 pi squared. Math, cube root, answer button. Do you get 422,50474? Yep. So 4.23 times 10 to the 1, 2, 3, 4, 5, 6, 7. They're fairly far out there. But that radius, which is all along the, by the way, also, you'd have to be doing this right along the equator. It does you no good if you're rotating every 24 hours but not in line with the Earth. That wouldn't really help. That's prime real estate. Our GPS satellites are there. A lot of our communication satellites are there. And they're high enough up that the idea is we can spot them from anywhere on the planet. Okay? Your homework is, hey, that's the end of the unit, but I got a couple of cool videos to show you. You can also now do every question on the ultimate circular motion and gravitation review.